Hello everyone, welcome. Sorry, just let me check if my stream is working or not. Then I will start. Just give me a moment. Uh, yeah, it's working. Yeah, I'm audible also. So let's start. Today I am starting with another chapter, moving charges and magnetism. Obviously, another super important chapter in terms of your PU board, in terms of your KCET exam. Both ways, this is one of the most important chapter from PU board. You can expect some derivations from for your KCET preparation. You can expect at least 4 questions coming from this chapter, if not more. Right. So this is a super duper important chapter, and I am planning to close it in 2-3 parts, obviously. So first, today we are going to discuss mainly about Lorentz force and moving charge. Okay, so let's see. So if you look into the chapter construction, you will see that here we have Lorentz forces, we have motion of a charge in a magnetic field, magnetic force on a current carrying conductor, magnetic field due to a current element and its applications. Okay, so in Biot-Savart's law, we have magnetic field due to a straight conductor and circular current carrying loop. Okay, other than that, we have also a comparison between magnetic field and electric field. We also have Ampere's law, applications for straight conductor, solenoid, force between two parallel currents, torque on a rectangular current loop, current loop as a magnetic dipole, galvanometer, ammeter and voltmeter conversion. So these are the 3 major parts. So today's session will be mainly focusing on this portion, Lorentz force, motion of a charge in a magnetic field, magnetic force on a current carrying conductor, etc. These will be our major focus, obviously Lorentz force being the primary drivers, right? And in the during the live session, if you have any questions, any comments, please feel free to ask me. Finally got rid of this after finishing KCET. Even long of this chapter names remind me of Thomas. Fresh prawn. Yeah, you are privileged, I will say. So after KCET counseling, which college did you receive? Please let me know that as well in the comment. Right? Which college you got? Yes, this is this can be little handful if you are not started with the proper approach at the beginning at this time, because most of you initially struggle with electric charges and field only, and then you lag behind with other chapters, and when the exam comes, when you open the chapter, it completely blanks your mind, right? Okay, so let's see. So what all we can do? First, we will start with basic introduction. This introduction part is actually from your class 10th chapter, magnetic effect of electric current. If you remember, some of you may have remembered, some of you may not remember it properly. Okay, so if you remember that there was a current carrying wire. Okay, let me just do it. So there was a current carrying wire, right? So in the current carrying wire, you had a cardboard like this. You placed it, and in this cardboard, what you are getting, you are going to get. I don't know why my screen is. Wow, RNSIT. Congratulations. Great. Hello, Sahil. Right. So, you may have done this experiment in your class 10th, or maybe you have just studied it without doing the experiment. Actually, it was supposed to be demonstrated to you by the teacher. Most schools do not do that. They just some of them nowadays show some videos. Some of them actually perform it. So here we had a current carrying wire connected to some battery somewhere, and in the there is a cardboard. In the cardboard, you have some iron filing, that is the some dust, iron dust, which is placed on this cardboard. You tap it and you observe that all the iron filings, they arrange in the circular order around the wire, right? I hope even if you have not performed the experiment, you remember the theory. Okay, you remember the theory portion of it, because that was one of the interesting part. Now, instead of having a current, even if there is a charge, moving charge, okay, even if there is a moving charge, single charge particle, even if it is moving, it will also produce its own magnetic field. So, current carrying conductors or a single moving charge particle, it also produces its own magnetic field. So, basically current is what? Current is moving charges, electrons moves, and because of the motion of the electron, you get a electric field sorry, not electric field, magnetic field around the wire, right? So, because of the motion of the electron, you are getting magnetic field. Similarly, if you have only a positive charge which is moving, in that case also you will get a magnetic field. Negative charge, positive charge, any charge, if charge is in motion, it will produce a magnetic field, and later on we will see in certain cases it will also produce an electric field as well, okay, and that creates a lot, something completely different, but for now moving charge produces a magnetic field, okay, and magnetic field means you require a magnet, and using that magnet you can determine the dimensions, direction of the magnetic field as well. So, here is a small example. Here dot represents out of the paper. Dot refers to out of the paper. Those who do not know, dot means out of the paper. So, if you see, these symbols are very common now nowadays from now on. So, if you see this, this refers to out of the paper, out of the page, out of the screen. That means this refers to something which is coming out in this direction, okay, because obviously this is a two-dimensional plane. How can you show something which is three-dimensional? Okay, so in that case people are creative, so they have taken this is the direction out of the page. So, in that case we will represent it using a dot with a circle, and if something similar with a cross is there. So, if you are someone who is confused, sir, what is dot, what is cross? Now, if the cross symbol is there, cross symbol, you remember, it is same as like a dart board, okay. You may most of you may have played when you were a kid, a dart board, you are throwing darts towards some target. So, this is the target. Target means what? That is why there is a cross. So, basically you are throwing something, it is going into the page. This is going into the page, right? So, this is very, very, very helpful. In many cases we will just draw cross, and in some cases we will just draw dots. So, dot means into the page, dot means out of the page, cross means into the page. So, just the direction of arrow is different, okay, out of the page or into the page, right? Based on the dot or cross, you can actually find the direction, right? Now, let us move on and see what we are discussing. So, here if you see that here a current is coming out of the page, and the magnetic field is oriented like this. Like electric field, magnetic field also have lines. We will see that in future, but not here. But yes, magnetic fields are also there, and if you put a magnet, the magnet will orient itself along the magnetic field lines, okay. So, if you point a magnet, the magnet will point in a particular direction. From there we can say that, okay, that means this is a organized thing. That means there is a magnetic field which is developed by this current carrying wire. If you switch off the wire, the magnets, all of the magnets rotate and goes back to original north south position, right? They are magnetic needles. Magnetic needle means small compass like thing. If you place it in near a magnetic field, it orients itself, it changes its direction. If it is there is no electric field present, then it points towards original north and south, magnetic north and magnetic south direction. But if there is a magnetic field present, it moves very easily. That is why it can be used to detect whether there is a magnetic field present or not. Okay, that is why this is called magnetic needle. It is a very small button shaped object, okay. It has a small magnet placed inside it. Like a compass. Compass is a bigger version of the magnetic needle. Compass generally do not deviate too much with small changes in magnetic field. It mainly point towards north and south direction. But needles, they are sensitive. They change their direction very quickly based on external magnetic field, presence of external magnetic field. Okay, so into the page, the orientation is like this. Okay, and out of the page, the orientation is like this, and into the page, the orientation is like this. Okay, we will see that everything, we will see the direction of current, etc., magnetic field, etc. You have done it in the class 10th. We will do that also in future, but for now let us understand what will happen, okay, if you keep a moving charge in the presence of an external electric field and magnetic field. So we have seen that moving charge produces magnetic field. Okay, moving charge produces a magnetic field, and a charge also have an electric field, right? If you keep a charge in an electric field, it experiences a force. If you remember first chapter, the force acting on a charge was given by Q into E, right? That was the force, static charge. Now if the charge is moving also, will there be any change on this force? It will not change. If there is an electric field, even if there is a moving charge, the charge will still experience this force, and the direction of this force is based on the sign of the charge. If the charge is positive, it will experience a force in the direction of electric field. If the force is charge is negative, the force is in the opposite direction of the electric field. So that is fixed. Even if the charge is moving, unless and until it is moving very fast, that is called relativistic motion, the charge will still experience the same amount of force, F is equal to Q into E. Okay, so that force is there, and now for this chapter we call it electric force. Let us call it electric force. So electric force will act on a charge whether it is static or it is moving. Now moving charge on the other hand produces a magnetic field. So if you keep a static charge in a magnetic field, it will not experience any force because of the magnetic field, because so only remember, if the quantities are similar, then only there will be some interaction, because electric field will interact with the charge, because charge also have a electric field of its own. Okay, that's why two electric fields basically interacting with each other. So I have, say, 100 rupees. I am going to visit a shop. I will say that give me some sweets. I will pay you 100 rupees. Okay, if I do not have any money, if I go to the shop, give me sweets for free, the shopkeeper will say, go home, eat your own sweets, make your own sweets and eat there, right? So the exchange happens only when you have something in return, right? So electric field and charge, they interact with each other because the charge also have its own electric field. So its own electric field and the external electric field, they both interact with each other. Okay, if the charge is zero, net charge is zero, there will be no force, obviously. If the net charge is zero, there will be no interaction, because there will be no internal electric field due to the source charge. Source charge itself is zero, so there will be no interaction, no force acting on the charge. So the charge is important to experience the electric force. Without charge, the electric force will not be there. Even Coulomb's law also dependent on two charges. So charge is important to experience electric force. Secondly, magnetic field, when you are considering that a charge will interact with the magnetic field, in that case also, very important point, the charge has to have a magnetic field, right? Then only it will interact with another magnetic field. If the charge is static, then its own magnetic field is zero. It will not interact with another magnetic field at any case. So the one and only condition that charge must interact with the magnetic field is when the charge is moving, and there are few other conditions as well, we will come to that, but the basic first condition is that the charge has to move. Okay, if the charge is moving, then only it can interact with the magnetic field. Okay, a moving charge, because it has its own magnetic field, when you keep that moving charge inside a magnetic field, both magnetic fields of the charge and the external magnetic field, they interact between each other, and that's why the charge will experience a magnetic force as well. The magnetic force acting on a charge is given by Q into V cross B. So the magnetic force acting on the charge is given by Q V cross B. Now here this is very important. Normally for electric field we do not add vectors. Okay, we assume if it is positive, it will be in the direction of electric field. If it is negative, it will be opposite direction of the electric field. So in case of electric forces, the vector notation was not super strict. But for magnetic force, because it depends on velocity and there is a cross product there. Okay, this is the cross product. If you remember in your first PUC rotational motion chapter, you have learned a little bit about cross product. So there is a cross product. Cross product is possible only between two vectors. That's why when you are writing Lorentz force, make sure electric force and magnetic force both are represented with vectors, right? Both has to be represented with vectors, otherwise it has no meaning. Okay, so when you are studying electric force or magnetic force, when you are writing force due to electric field is Q into E, force due to magnetic field is Q into V cross B. So whenever you are doing that, you have to remember that they are vector quantities, so you have to write them in vector notation. Okay, you have to write them in vector notation. Now you can keep the electric force like this, the way I am writing, that is not mandatory, but the vector sign on both cases has to be there. Okay, so now when an object is subjected to different forces, okay, it can be same direction, it can be opposite direction, it can be at an angle. How to find the resultant of the two forces? We use vector addition, right? Two vectors acting on an object, it can be at any angle. Suppose this is magnetic force, this is electric force, and this is the charge particle. So when two different forces acting on a particle, we have to apply vector addition to find their resultant, and that resultant force is called Lorentz force. So Lorentz force is the resultant force of magnetic field as well as electric field when they act on a particle. Here we have a particle Q, a magnetic field is acting and some electric field is also acting. So when you are adding them, it has to be added vectorially. Now Q is charge, it is a scalar, it can be taken common. So the resultant resultant force acting on a charge is given by Q into E plus V cross B. Okay. Now, so this is the Lorentz force. The question that will come, what is Lorentz force? Write its expression and explain the terms. So Lorentz force is the force acting on a moving charge particle in the presence of external electric and magnetic field. External electric and magnetic field, in the presence of external electric and magnetic field, the charge particle experiences a force, and that is called Lorentz force. Now, what else? The expression for Lorentz force is given by F is equal to Q E plus V cross B. Q is common, right? So this is the expression. You have to write E is electric field, V is magnetic field, V is the velocity of the charge particle, Q is the charge on the charge particle, and F is the resultant force. So these are the things that you have to mention while writing the Lorentz force. Now next, a few points that you have to remember about this force. Okay, force on a negative charge is opposite to that of the positive charge. Same thing as electric field as well, but here the cross product is there. So if the force due to positive charge, suppose in this direction due to positive, then due to negative it will be in the opposite direction. Okay, the vector product makes the force due to magnetic field vanish or become zero if the velocity and magnetic field are parallel or anti-parallel. So as I mentioned, charge particle has to move. V cannot be zero. That is condition number 1. Second condition is that if V and B are parallel. So suppose the particle is moving in this direction and the magnetic field is in this direction. Okay, this is case number 1, and case number 2 is velocity is in this direction and magnetic field is in the opposite direction. In this case also, in both cases, magnetic force acting on the charge particle will be 0, because the cross product between two parallel vectors, suppose two vectors A and B are there, okay, and A and B are parallel to each other, then their cross product becomes 0. Why so? If you remember that cross product, when you take the magnitude of the cross product, okay, it comes out magnitude of A, magnitude of B into sine theta, right? And in case of parallel or anti-parallel, for parallel theta is 0, for anti-parallel theta is 180 degrees, sine 0 is 0, sine 180 degrees 0. That's why when you are taking cross product of two vectors, if they are parallel, their cross product is 0. okay, because sine theta for theta equals to 0, sine theta is 0. Okay, here theta is 180 degree for anti-parallel, and in that case also sine theta is 0. For theta and theta 0 or 180 degree, in both cases sine theta becomes 0. Okay, so this is one very important point. So there might be MCQ questions based on this. The force, magnetic force or Lorentz force acting on a charged particle will be 0 if velocity is 0, magnetic field and velocity vectors are parallel, magnetic field and velocity vectors are anti-parallel, none of these or all of these. Okay, here it will be all of these. So you have to identify, okay, all three conditions where magnetic field can be 0, the Lorentz force can be 0. That means all of these will be the answer. Very important point to remember. If V is 0, or if V and B are parallel or anti-parallel, then also their cross product will be 0. Right? The magnetic force is 0 if charge is not moving, then magnitude of velocity is 0. Only a moving charge feels the magnetic force. As I mentioned, only a moving charge feels the magnetic force, because moving charge have its own magnetic field. So only a magnet can attract or repel another magnet. That's why when the charged particle have its own magnetic field, then only it will interact with an external magnetic field. If the magnetic if the charge do not have any magnetic field on its own, then it will not have interacted with the magnetic field. Right? That is very clear. Thank you, HVJMN. Okay, so that is very important. That is super duper important point to remember, that magnet will interact with another magnet. Okay, if you just leave a magnet, it will not interact with the non-magnet. If it is a magnetic particle or magnet, then only it will interact. For moving charges, it has to be magnetic, then only it will interact with external magnetic field. So moving charge possesses the magnetic field, and moving charge, because it possesses a magnetic field, it will interact with external magnetic field. That is point number 1. So static charge do not have any magnetic field, it do not interact with another magnetic field. Secondly, the magnetic field and velocity vector, even if the charge is moving, still the magnetic force can be 0 if V and B are parallel or anti-parallel. Okay, why? Because when you are doing cross product, you have to recall that cross product gives you a sine theta as exponent, and if you are considering parallel vectors means theta 0, sine theta 0. Anti-parallel means their opposite direction. So anti-parallel, basically for vectors, anti-parallel refers to opposite directions. So in that case, the angle is 180 degree, right? Anti-parallel means this is the direction, this is another direction. This is anti-parallel, so angle is 180 degree. Okay, so that is 180 degree. So theta 180 sine 180 degree is still 0. That's why in both cases you are going to get sine theta 0. Now let's see one question that was asked in one of the previous year. I forgot to mention the year over here. A proton moves with a velocity of 5 into 10 to the power of 6 j cap meter per second through the uniform electric field E is equal to given some value, and the uniform magnetic field B given by another value. The approximate net force acting on the proton is. So first you have to calculate the approximate net force or approximate magnitude of force. That is more important. Okay, first we have to calculate, obviously electric field is given, proton. So charge of a proton. So what is the charge of a proton? Charge of a proton is basically same as electron, only difference being it's a positive charge. Okay, charge of a proton, don't be afraid if you see charge of a proton etc. Proton has same charge as electron. Sometimes we forget, electron has charge 1.6 into 10 to the power minus 19. Proton will also have the same charge, but it is positive in sign. Okay, now electric field is given. So what is the electric force? So basically first we have to calculate the electric force. Okay, then you have to calculate the magnetic force, then you have to find their sum, and then we have to take the magnitude. It's a long process, little longer, lengthy question, okay, but it came in KCET exam, so you need to, and it is a very good practice actually. So what is electric force? Electric force is Q into E, okay. So Q into E is basically 1.6 into 10 to the power of minus 19 into 4 into 10 to the power of 6 into this 2 I cap plus 0.2 J cap plus 0.1 K cap. So there is an approximation. I will tell you about the approximation as well, but not here. So 1.6 into 4 is 6.4 into 10 to the power of minus 13 into 2, or let me keep this like this only for now, because this charge will be common anyway. So let's keep it like this for now. Okay. What about the magnetic force? Magnetic force is important. So let's calculate the magnetic force. Magnetic force is FB is equal to Q V cross B. Okay. So V is given by, Q is obviously 1.6 into 10 to the power 9. We will take it common, so don't worry. V is given by 5 into 10 to the power of 6. 5 into 10 to the power of 6 J cap cross 0.2 I cap plus 0.2 J cap plus K cap. Now you need to remember two things. First of all, when you are doing cross product between two same vector is 0, because I cap and I cap, they are in the same direction, so they are parallel. That means their cross product will be 0. Okay. Similarly, J cap into J cap will be 0 and K cap into K cap will be also 0. Now here only this one is required, but for your information you need to remember, when you are doing cross product between two equal unit vectors, that becomes 0. Okay. So here this J cap and this J cap will be 0. So we do not need to consider this term at all. This is J cap, this is also J cap. So their product should be 0. So we do not need to consider anything. So let's take all the constant outside. Q into 5 into 10 to the power of 6 into 0.2. They are all constant. It will come out. So here we have J cap and cross product I cap plus K cap. So why I have not written J cap here? Because J cap into J cap is 0. So writing J cap in this equation does not make any sense. So that's why I am just keeping it. For dot product, it is opposite. Remember that dot product, I cross or I dot I is 1. That's why student gets little confused sometimes. I dot I is 1, J dot J is 1, K dot K is 1, and when you are doing between two different dot products, I dot J is 0, I dot K is 0. Okay. So for dot product, it is exactly opposite. In case of cross product, between two similar cross is 0, and other two products, they are not 0. Okay. I cross J is not 0, I cross K is not 0, or J cross K is not 0. But in case of dot product, I dot I is 1, everything else is 0. I dot I is 1, J dot J is 1, K dot K is 1, everything, any other cross between two vectors will be 0. Okay. That is super important. Sometimes student confuse here. Now how to remember? First is obviously we are doing, so if you break this bracket, if you want to break the bracket, what you do? Okay. This is the cross product bracket. So if you have normal, say A into B plus C, what do? You multiply between these two, AB plus AC, right? That's what you do. So similarly here, what you have to do? You have to find So this constant is there, and here you have to do same thing, j cross I cap plus j cross k cap. Okay, j cross I cap plus j cross k cap. Right? I think yes, both of them are same. So j cross I cap and j cross k cap. Now you have to find these quantities separately. What is this? How to find cross product between two unit vectors? So remember this, I, j, k, clockwise rule. So if you are crossing I cross j, you are getting k. Okay, I cross j, you are getting k. J cross k gives you I. J cross k gives you I, and k cross I gives you j. So any cross between these two always go in the clockwise direction. I cross j is k. Okay, j cross k is I. K cross I is j. But sir, here we have not I cross j, but we have j cross I. So I cross j is circular order. Now if you move in the anti-circular order or anti-clockwise order, in that case, when you are going in the opposite direction, that will give you the negative. Okay, so j cross I will give you minus k, I cross k will give you minus j, and k cross j will give you minus I. Okay, so if you are going in the positive direction, everything is positive. This is the positive direction. So I cross j gives you k. Okay, j cross k gives you I, and I cross k gives you j. This is the positive direction. And negative direction, if you are going in the opposite, then it will be just sign will be opposite. Okay, just remember that. So here we have j cross I. So j cross I is nothing but minus k cap, and then we have j cross k. So j cross k is plus I cap. Okay, so this is a vector product. So you're after doing the product also, it will be a vector quantity. Okay, so basically, even though we are discussing about moving charges, it is a mini vector class as well. Okay, so q into 5 into 0.2. Let me simplify this. 5 into 0.2 is 1. Okay, 5 into 0.2 is gone. So we have q into 10 to the power of 6 into this. So this is the magnetic force. Electric force was given by this. Let me write it in terms of q only. Okay, and this is q into 10 to the power of 6 into minus k cap plus I cap. So what is the sum of these two vectors? So Fe plus Fb, let's add them. So when you are adding them, q is common. Okay, you can see that 10 to the power 6 is also common. Now here we have this 4 into this entire thing. So 4 into this entire thing, 2 I cap plus 0.2 j cap. Here no problem. Electric field will not cause any major problem. Magnetic field calculation is slightly tricky. Now magnetic field is minus k cap plus I cap. Right, there was only one was there, so that one multiplication you will get that. Now you simplify this, q into 10 to the power of 6. Q is 1.6 into 10 to the power of minus 19, and if you multiply with 10 to the power 6, you get 1. So when you multiply 10 to the power 6, you get 1.6 into 10 to the power of minus 13. So this is 1.6 into 10 to the power of minus 13. Now 8 I cap plus 0.8 j cap plus 0.4 k cap minus k cap plus I cap. Okay, or it will be 1.6 into 10 to the power of minus 13, 9 I cap plus 8.8 j cap minus 0.6 k cap. Okay. Now, what is the magnitude of this? This is the vector quantity. This is the vector form. How to find magnitude of a vector? If you remember, magnitude of a vector was calculated as, so magnitude of a vector is basically given by square root of ax square plus ay square plus az square. Okay. So from here, if you are trying to calculate this from here, what you can do is, this is sorry, not here, my mistake. So this is the x component, this is the y component, this is the z component, right? So you basically need to square them and add them, but there is a shortcut method. You don't need to do that for this particular problem, because if you see that this 9 is way bigger than 0.8 and 0.6. The 9 is way bigger than 0.8 and 0.6. So if you just do it, okay, for this problem, 9 square plus 0.8 square plus minus 0.6 square. Obviously, minus sign do not pay any attention in this when you are calculating the magnitude. You will see that these are very, very small compared to this 9. That means when you are taking the square root of this, it will turn out to be 9 only. So the approximate value will be 9. So that is the method that you need to know. After solving this much, you don't need to waste any of your time calculating the exact magnitude. So what you can do, 1.6 into 9, which is 9, 6 9s are 54. So it will be 9 plus 5.4, 14.4 into 10 to the power of minus 13. This is the magnitude. So 14.4 into 10 to the power of minus 13. Now there is, you don't need to guess the answer. The correct answer is, of course, 15 into 10 to the power of minus 13. Now this is a lengthy problem, as I mentioned. In KCET every year there are 2 to 3 questions which are lengthy. Okay, those questions, if you are well versed with vector geometry, vector addition, subtraction, multiplication, etc., then only attempt those. Otherwise, you can obviously skip. Not all lengthy questions will be vector based, obviously, but here if you see such questions where some vector forms are mentioned, and if you think that it will not be able to solve it quickly, then you can skip those questions initially, and then at the last you can guess those. But remember that there will be 2 to 3 questions which will be lengthy, not difficult but lengthy. Okay, so those 2-3 lengthy questions require extra time. Now those extra time you have to save from the questions which requires very less amount of time. Some questions you can solve it just by reading it. That should be 10 seconds maybe, or 20 seconds. Okay, to make sure, double check, 30 seconds. Okay, so within 30 seconds you need to solve at least 30 questions. 25 to 30 questions are like those. Okay, so each of those questions you are going to save a lot of time. So whatever 30 second, 10 second, 15 second, 20 seconds, whatever time you are saving on those questions, they gets added up, and the teachers, the examiners expect you to save the time at least 4-5 minutes from other questions, and then invest that in this lengthy question. Okay, so if you have prepared well, then only you will be able to attempt those lengthy questions. But this question did came in the past, and also based on Lorentz Force, right? Okay. Now, before I continue, just wanted to tell you one very important point that you may have missed. So when you are, if you go to the description section of this video, you will see something very important part. Okay, if you come to the description section of this video that is going on live over here, okay, you will see very important thing. Click on this more button, and here you will see that join free ACE KCET 2027 course. Once you click on here, okay, you will be redirected to this page, and once you are in this page, you will see that you can join our ACE KCET 2027 batch absolutely free of cost. You click on this buy now button, and then you need to register using your mobile number and email ID. Once you register using your email ID and mobile number, you will be granted access to this page, and once you click over here, you will get all the lectures that we are doing on our YouTube channel. But here very importantly, there are two things that you need to consider. First of all, in YouTube, there are a lot of distractions. Okay, some other ads, etc. pops up. Here, it will be completely no distraction, and no other channel recommendations, etc. will come to your feed. Okay, and your mind will be stay focused if you are studying from here, right? And once you are studying from here, you will also get the class notes as well. Okay, you will get the class notes. Okay, class slides over here, right? All the notes that you are preparing for, all the notes, etc., practice questions, everything will be provided in here. So if you are really serious about your KCET preparation, what are you waiting for? This is absolutely free, absolutely for you. So do click on here and start learning today, right? Now let's move on with the motion of a charge in a magnetic field. Okay, so now what we have done so far, we are discussing with forces. Okay, Lorentz force was there, and if there is a Lorentz force, the charge will experience a force, right? Now what this force will do, that is very important. So for example, if the electric field is there, a static charge is there, there will be a force. The electric charge will start accelerating either in the direction of the electric field or in the opposite direction of the electric field, right? That's what happens. But in case of magnetic field, it does not do exactly the same like electric field. First of all, the charge has to be in motion. So charge is already in motion. Okay, when the charge is already in motion, so it will accelerate in some direction, right? So when you are trying to find the cross product, again another vector calculation. So if you are finding the cross product, suppose two vectors, say vector A, and vector B, they are acting at some direction. Okay. Now when you are trying to find, say, A cross B, then what will be the direction of these vectors? Okay. In case of electric field, one was scalar, one was only one vector was there, so there was no problem there. But in case of magnetic force, one is velocity, another is magnetic field. Both are vector quantities, right? Both are vector quantities. That means there will be a force that will act on this system. So how to find the direction of this force? So when you are doing cross product of two vectors, how to find the direction? The direction is very important. First, which vector is first? Here, for example, A is first. So first you point, you take your hand, okay, you point all your fingers towards the first vector. You point all your fingers towards the first vector and then curl your fingers towards the second vector. Okay, so A cross B. So this is A. Now we are curling towards B, and then my thumb is pointing towards the cross product. Okay, the direction of the cross product is in this direction. So A cross B gives me this vector. Okay, if you are doing, say, suppose V is in this direction, V. Magnetic field is in this direction. Now we are just reversing it. Okay, so we are trying to find V cross B. How to do that? First, you have to point all your fingers towards the first vector. V is first, this is first, this is second. Okay, if you point it like this, you will not be able to move towards the second vector easily. So you have to point your fingers in the direction of the first vector and then curl it towards the second vector through the acute angle. Okay, not the obtuse angle. You have to use the acute angle only. So when you are pointing your fingers towards the first vector and then curling your fingers towards the second vector, then your thumb points towards the cross product. Cross product is V cross B, so it will be into the page. This is into the page, into the page. Here this is out of the page. This is out of the page. So this is very important point to remember when you are doing cross product of two vectors. The direction is not that simple. You have to use the right hand thumb rule. Right hand thumb rule to calculate the direction of the vectors. Okay, A cross B, this is the direction. B cross A, this is the direction. Okay, that's how you calculate the direction of two vectors. So here, when a charge is moving in a magnetic field, the direction of force is basically perpendicular to both V and B. Okay, the direction of force is perpendicular to both V and B. Okay, now if the vectors are themselves perpendicular, for example, V say in this direction, B is in this direction, they form a triad. Okay, V cross B, so that is into the page, so they form a triad. This is the force into the page. Into the page, they form a triad, and the triad, what they do, V, B, F, everyone is perpendicular to each other, right? And that means the motion, only possible motion in that case is a circular motion. If V and B are perpendicular to each other, the force will also be perpendicular to both of them. They form a triad, and that triad means the motion, only possible motion is a circular motion. So here in this diagram, it was slightly differently depicted. The magnetic field is taken into the paper. So cross referred to into the paper. So magnetic field is going in. Okay, cross means into the paper. As I mentioned, cross refers to into the paper. So the magnetic field is into the paper. Okay, the particle is moving along this. So V, first you have to point V, then B. So this will be the direction of the force, and that force is considered to be a centripetal force, and because of this centripetal force, the particle will move in a circle. So a charge moving in a uniform magnetic field will experience a force. This force acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. If velocity has a component along the B, now suppose they are not directly perpendicular, okay, the angle is not 90 degrees. So if V and B are perpendicular to each other, then this happens. But if they are not perpendicular, so this is the direction of V, this is the direction of B, they are not perpendicular. The angle between the velocity vector and B is not 90. So in that case, you can divide this velocity vector into two components. One is perpendicular, one is parallel. Okay, now perpendicular component is actually what it is doing, it is making it move in the circular motion. And the horizontal component, it is actually not changing with time, it is remaining constant, because parallel component of magnetic field means it is actually not contributing, their cross product is 0. So this parallel component actually taking the charge in the forward direction. So both kind of motion happens over here. The perpendicular component tries to rotate in a circular motion. The linear component or the parallel component, it takes no, you don't have to move in circle, you come with me, you move in a straight path, and both motion happens simultaneously, and that's why the motion is called a helical motion. This is a helical motion. Now what is a helical motion? If you take a spring, okay, if you take a spring, you have seen a spring, right? Inside a pen, we used to play with our pens, inside the pen there is a spring, right? So in that spring is basically, the shape of that spring is a helix. Okay, shape of that spring is helix, and any particle moving along the helical along a curve of a helix, that motion is called helical motion. Okay, so when the angle is 0 to, when the angle is greater than 0 but less than 90, you get this motion, and this is when the theta is equals to 90. Theta is 0 means no motion, so it will just move straight without any deviation. If the angle is 0, it will move in a straight line without any change, no acceleration, nothing, force is 0, and we are not considering that. We are considering the motion where it is moving, okay, and if the angle is 90 degree, it is moving in a circular path. If the angle is not 90 degree, it is moving in a helical path, because there are two components, two brothers. Okay, velocity becomes two different brothers. One brother takes it in a circular motion, one brother says no circular motion, move, come with me, come in a straight path. Okay, so both are happening simultaneously, like projectile motion, if you remember. So one is taking it upwards, one is taking in the forward direction, and you get a parabolic motion. Here it is helical motion. Okay. If the velocity has a component along B, this component remains unchanged, as the motion along the magnetic field will not be affected by the magnetic field. The motion in a plane perpendicular to B, as it is a circular one, thereby producing a helical motion. So, there is a circular motion, okay, and there is a straight line motion. Combining these two motion gives you a helical motion. Okay, helix. This structure is called helix. Helix is like this. I don't know what happened. Color change. This will be helix. So, circular is also happening and linear motion is also happening. So, circular and linear combined together is called a helix. Okay. Now, let us find the few things about this motion, which is first, obviously we are not helical motion is just for your MCQ questions. If the angle is between 90 degree and 90 degree and 0 degree, it will be a helical motion. So, that is very important point to remember. So, 0 degree, between 0 and 90 and 90, these are the three angles that you need to remember. Any other angle, any other options are actually given as a distraction, that is a wrong option. Okay. So, you need to remember three cases. Angle 0 means straight line motion, angle 90 means circular motion, angle between 0 and 90 it is a helical motion. Okay. 90 and 180 also same logic, but generally does not come in the exam. 90 to 180 will also be helical motion, 180 is again straight line motion. So, that is how a charged particle will move. Straight line motion means force is 0. Okay. So, there was the MCQ question, at the angle between velocity vector and magnetic field is 45 degree. What kind of motion it will exhibit? Circular, linear, helical, parabolic. You have to remember it will be helical motion. So, based on the angle theta value, you have to identify what type of motion it is. So, that is a very important point for MCQs, board exam, KCET exam, everywhere it might be asked. Okay. Now, our target is to find the radius when the angle is 90 degree. If the theta is 90 degrees, then what will be the radius of this motion? Okay, this is the circular motion when the charged particle is kept in a magnetic field and the velocity vector and the magnetic field, they are perpendicular to each other. Okay. So, magnetic field is again into the page of the paper and velocity vector is in this direction. So, velocity and magnetic field, they are mutually perpendicular. So, there will be a mutually perpendicular force, magnetic force, which will act like this. Okay. Now, we know that what was the Lorentz force, magnetic component of Lorentz force, it was given by F Q into V cross B. Right. Now, if you write it in scalar form, what is the magnetic force? Scalar form in magnetic force, generally scalar form, we do not write it like this. We write it simply F equals to Q V B sin theta. Right, this is the normal form. Now, if theta is 90 degree, then sin theta becomes 1. So, the force becomes QVB, only QVB. Okay. And this force actually makes the particle move in a circular motion because this acts as centripetal force. Okay. So, this is nothing but centripetal force. And what is centripetal force? Centripetal force, if you remember in your first PUC, the particle moving in a circular motion, okay, there is a centripetal force which acts towards the center of the motion, which is given by mv square upon r. Formula remains same even in this case. So, basically we need to compare these two quantities and find the radius. Okay, few things you have to find the radius, angular motion and time period. These are the two things that you need to find. So, first we will find the radius. So, QVB equals to mv square upon r. So, if you remember the basic foundations, everything you can recall in the exam. You don't need to remember or memorize everything. Just remember QVB is the Lorentz force, mv square by r is the centripetal force. I need to simplify them and find the value of r. That's it. You don't need to remember it. You practice it. once or twice, see that if you are able to solve them or not, but you don't need to. Hi, Mahantesh Naik. So, you don't need to memorize all the lines. You just need to understand how this is achieved. If you remember the steps, if you try to memorize the steps, that will take a very, very long time. And if you are trying to memorize everything, and your basically you actually make mistake in somewhere in between, and you lost everything. But if you know that this force is nothing but a centripetal force is given by mv square by r. This force is qvb. I need to compare them, simplify and find r. That's it. If you remember that, then you can solve it on your own. But that much calculation ability you have, right? So this v and both are same v. Obviously, the particle moving in a circle cannot have two different velocities. So one of the v gets cancelled. Now from here we get r equals to mv upon qb. This derivation is worth of 3 marks, not 1, not 2, but 3 marks. Okay, easy derivation, but again the formula for this is used in KCET. The derivation is for PUC, the formula is for KCET. This formula you have to remember. If you can, you can remember it. I generally do not remember it. I know this is the basic relation, and I try to calculate it on the go. Okay, so if you remember it, it will also stay with you for KCET exam. Now, as I mentioned, what is angular velocity? For angular velocity, omega is given by sorry, not omega, let me write the velocity. V equals to r into omega. Okay, this is the rotational motion. From rotational motion, linear velocity and rotational velocity, the relationship between linear velocity and rotational velocity is given by v equals to r omega. Okay, now we have calculated the value of r, we know the value of v, so we just need to calculate omega. Omega is v upon r. Okay, and what is the value of r? R is mv by qb, so it will be v divided by mv by qb. Okay, so that means this is the main division, this is division of division, so this will go up. You get v into qb upon mv. This v cancels and you get angular velocity is equals to qb upon m. Okay, qb upon m. Now time period is given by 2 pi by omega. Okay, time period is given by 2 pi by omega, so it will be 2 pi m by qb. 2 pi m by qb. Okay, and if you are talking about frequency, normal frequency, the frequency is omega by 2 pi. So that will be qb by 2 pi m. Now in the past syllabus, this was called cyclotron frequency. Okay, this was called cyclotron time period. Cyclotron is no longer part of the syllabus. Okay, this is an application of this process. Okay, cyclotron is an application of this process, but that cyclotron is not part of the syllabus, so I am not going into it. But if you somewhere come across the term cyclotron, remember it is basically an application where a charged particle is accelerated inside a particular magnetic field. Okay, if you have heard about something called LHC, Large Hadron Collider, okay, which was developed in the part of United Nations, United countries, okay, EU. So they have developed a system where there is a very large circle is there, and there are a lot of magnets are placed along this large circle, okay, which is actually underground. Okay, and particles are actually accelerating. Charged particles are accelerating inside it. Okay, in the same way you can accelerate the charged particle, okay, and you can select the velocity, etc., etc. There are a lot of processes there, but the large particles, number of particles can be accelerated inside this tube. There is a tube here, okay, and through that tube you can actually accelerate the charges, and you can make them collide with each other and then test what happens when they collide. So that is the main purpose of this design. So they are doing a lot of testing, a lot of particle simulations, etc. What happens when two electrons collide, what happens when two protons collide, or something like that. Okay, so that is which one? Which Ravi Belagavi, I think you have misread your name. Which one you did not understand? Tell me. Which part you did not understand? Tell me, then I will explain. If you are here, Ravi, and if you do not understand, you need to start watching from the beginning. If you just come at the middle of the lecture, you may not be able to understand, right? So try to join as soon as the lecture starts. Right? So if you just come here to say hi, okay, first thing you said here after coming is hi, hi, hi. And then you said I cannot understand. So your purpose is to say hi to each other. Okay. You are not, your main purpose is not to learn and understand. If your purpose was understand, you have said I did not understand this. Okay. And then you spammed sometimes and then you left. This is not how you should study, Ravi. Right. Let's see one question. A proton, a deuteron and an alpha particle having the same kinetic energy are moving in a circular trajectories in a constant magnetic field. If Rp, Rd and R alpha denote respectively the radii of the trajectories of these particles, then first of all, what is given? There are three particles, proton, deuteron and alpha particle, and their kinetic energies are same. Now, if you see here, the radius depends on mv. Radius depends on mv. What is mv, by the way? What is mv? If you remember what is mv, mv is mass into velocity. Mass into velocity is momentum. Momentum is denoted by small p. Momentum is denoted by small p. Right? This is mass into velocity is momentum. Right? Mass into velocity is momentum. So now if you see here, R can be written as momentum divided by Q into B. Okay, you don't need to, when any problem which is related to kinetic energy is given, then you always need to use this formula. So radius is momentum divided by Q into B. Okay, whenever kinetic energy is given, kinetic energy's best friend is momentum. Right? Kinetic energy's best friend is momentum, because you can calculate momentum using kinetic energy, you can calculate kinetic energy using momentum. Okay. So what is the relationship between momentum and kinetic energy? Otherwise you might feel that, okay, kinetic energy is given, velocity must be same. No. These three particles, the main challenge with this question is proton, deuteron and alpha particle, they have different masses. Each of them have different masses. So even if their kinetic energies are same, you will not be able to find how they are related to each other without knowing their masses. Okay, that is the major challenge. So velocity is not same over here. Even if they have same kinetic energy, because of their different masses, kinetic energy is given by half m v square. Kinetic energy is given by half m v square. Now, if you multiply m on both sides, you get m into kinetic energy equals to half m square v square. Now, let's borrow this half from right hand side to the left hand side. You get 2mk equals to m square v square, or m into v is equals to square root of 2m ek. Right? You take the square root, you get the momentum. So momentum is equals to P is equals to square root of 2m ek. Now, if you see that here we are able to establish the relationship between momentum and kinetic energy, how they are related to each other. Okay, so we can see that here radius of any particle is proportional to its momentum and its charge, magnetic field being constant. Okay, proton, what is the charge of a proton? Proton has a positive charge, that's same of an electron, right? So plus E. Its mass is same as single proton, so I am writing that with m. So for proton, charge is, let me write it that charge mass. Let me write a table for you. Okay, you don't need to know the exact mass, don't worry. Okay, so for proton, the charge is plus of electron. Mass say m. For deuteron, the charge is same that of a proton. Okay, deuteron basically isotope of hydrogen. Okay, consisting of one proton and one neutron. So assuming that it is a deuteron ion, obviously deuteron ion, that has to be mentioned over here, deuteron ion. Otherwise, this question does not make any sense. So deuteron ion basically have same charge as electron, because obviously it has only one proton and one neutron. Okay, but when it comes to mass of deuteron is twice that of a proton. Okay, mass of deuteron is twice that of a proton. Why? Because deuteron has one proton, one neutron. Okay, deuteron has one proton and one neutron. So 1 plus 1 is 2. Next is alpha particle. Those who do not know alpha particle, you may not have studied it in physics so far. Okay, but you may have studied in chemistry. So I am assuming you know. If you don't know, I am telling you, alpha particle is doubly positive helium ion. Helium, element helium. So it's a doubly positive helium ion. Doubly positive means both electrons from helium are taken away. Helium has 2 electrons, both electrons are taken away. So that's why it is called doubly positive helium ion, which is a alpha particle. So it has double charge of a proton, so it will be plus 2e. For helium, it will be plus 2e. For mass of helium, it is 4 times that of a proton. Helium has 2 protons, 2 neutrons. So its mass is 4 times. This is the major problem. If you know this, this is a piece of cake. Okay, so let us find what is R alpha, or sorry, R proton first. So R proton is what? R proton is some constant. We are assuming the constant to be 1. Charge of a proton is E, and momentum. Momentum means what? Momentum means square root of mass m. Momentum is dependent on square root of mass m when kinetic energy is constant. Kinetic energy is constant, same kinetic energy is same. So Ek is same, 2 is constant anyway. So that means we can write this one is actually equals to root m. Momentum is proportional to square root of m when kinetic energy is constant. Okay, so now we will write it here. So in division we have charge of an electron and mass is m, square root of m, into some constant. That constant we are assuming 1. Next, radius of deuteron. Radius of deuteron is, here mass is twice of that, but charge is same. Okay, and radius of alpha particle, mass is 4 times, charge is twice, so it will be 2 root m by 2e, 2 cancels, you get root of m by e. Okay, so if you see that these two are equal, this is bigger. Okay, these two are equal, this is bigger. That means R alpha and R proton are same, R alpha and R proton are same, and they are smaller than that of deuteron. If you see this option, R alpha equals to Rp and they are both smaller than Rd, so option 1 is correct. Okay, option E, option 1 is correct. Very interesting question based on alpha particle, alpha, deuteron, proton, etc. based questions did came in the past, even maybe not from this chapter, but based on this concept we have seen questions in the past, and it came multiple times. So you need to understand what is a proton, what is a deuteron, what is a alpha particle, what is a beta particle. Beta particle we will see in future. Beta particle is nothing but an electron. Okay, beta particle is nothing but an electron. So those things you need to understand. Charge, mass. Okay, mass for a beta particle or electron is very small, so you can ignore the mass of electron. But for proton, you need to understand proton, deuteron, tritium. Tritium has 3 times mass of proton. Okay, tritium has 1 proton, 2 neutrons. Okay, so this is the basic problem, very basic problem, and you should be able to solve it if you are practicing well enough. Okay, now let's move on with another thing, which is magnetic force on a current carrying conductor. Okay, you have now so far what we are discussing, we are discussing about force on a single charge, force acting on a single charge. Now we are moving on from a single charge towards a current carrying conductor. Okay, now we have a current carrying conductor and we want to find what is the force that acts on a current carrying conductor. So we have a conductor, some conductor is there, say the length of the wire is L, the cross sectional area is A, okay, and it is carrying some current I. Okay, it is carrying some current I. There is a magnetic field at some angle with this current carrying wire. Okay, you have to find the force which is acting on this wire due to magnetic field. If a single charge particle can experience force, the current carrying wire will also experience a force. Current carrying wire is what? Current carrying wire is a flow of electrons. Electrons are moving, and because electrons are moving, there will be a force acting on these electrons as well. Now, in the with what speed the electrons are moving? Electrons are moving with the speed which is called the drift velocity, right? The electrons are moving with the speed which is called drift velocity, right? Now, let us try to figure out what is the force. From Lorentz point of view, it says that force must be Q into V cross B. That is very simple. Lorentz says if there is a charge particle, if it is moving in a magnetic field, the force is Q into V cross B, as long as the angle is not 0 or 180 degree, right? Now, the main problem with this is that find the charge. Okay, here we have a certain length of wire. Okay, so it has certain amount of charge, and we know that one quantity which can find the charge, that is called charge density. Charge density. What is charge density? Charge density small n is charge per unit volume. Charge per unit volume, right? That is the charge density. Now, if n is known, then we can find this charge. So, our main target is to find this charge and then calculate the force. So, charge per unit volume is n. Okay, charge per unit volume is n. What is the volume of this conductor? Volume of this conductor is length into area. Okay, when you are considering a volume of a cylinder, I discussed in one of my previous lecture as well. If this is area, if this is length, okay, then length into area gives you the volume of this. Okay, it is applicable for any regular geometric shape, not only for cylinder, even for a cube also. Cube also, if you test that, you can find that as well. For a cube, we know that area of a cube is this is area, this is A, okay, and what is A? A is obviously A square. What is length? Length is another A. So volume is A square into A, which is A cube. So this formula, area into length, is applicable as long as the shape is regular. If it is irregular shape, then it will not be applicable. You need to modify that based on the shape. But yes, for a small regular shaped object, this can be applicable. So length into area gives you the volume. Here we have assumed simple cylindrical column. So definitely it will have a volume L into A. Now this is the total number of charge. Okay. So what is the charge then? Very simply multiply with charge of 1 electron. So this is the total number of electrons. Charge in case of conductor is basically electrons. So this is the total number of electrons. When you multiply with the charge of an electron, you get the total charge. Now we have to use it back over here. Okay. So N E A L, this is the charge, right? N E A L. Just we are organizing it because we will need it like this very soon. So N E A L, okay, and that becomes into V D, drift velocity, into B. Okay. Now this can be written as N E A B. This is the drift velocity, so I am writing it at V D into L cross B. Okay. Now this NEAVD, if you remember, current is given by NEAVD, right? In the previous chapter, current electricity chapter, we were discussing current is given by this formula NEAVD. Now one important point there was this current was not a vector quantity, but here this drift velocity is a vector quantity. So how do we adjust this vector? Okay, the vector from this drift velocity, it will be transferred back to the L vector. Length is a vector quantity. Length is a vector quantity, but length can be taken in both direction. It can be either in this direction or in this direction. So here we take the length vector in the direction of current. Okay, we need to take the length vector in the direction of current. Then we can successfully transfer this VD, the vector from VD to L, and we can write it as IL vector. Okay, we can write this as IL vector, and we can write this is IL cross B. So the force acting on a current carrying conductor is basically given by this simple formula L cross B. Do not confuse B cross L or L cross I, L cross B. It will be always L cross B. Okay, and if you write in scalar form, which is more popular, BIL sin theta. Bill sin theta. If you remember Bill sin theta. Okay, BIL sin theta. Okay, so this is the force that is acting on a charge current carrying conductor. Now if sin theta is 0, that is theta equals to 0, okay, force is also 0, right? Force is also 0. And if this theta is 90 degrees, okay, sin theta is 1, so the force is maximum. So current carrying conductor is kept in a magnetic field when the force will be maximum. Force will be maximum when the angle is 90 degrees. Okay, force will be minimum when the angle is either 0 or 180. 0 or 180, the force will be 0, or theta equals to 90 degrees, the force will be maximum. So, maximum will be when the angle is 90 degrees. Okay, angle is 90 degrees, force is maximum. And angle is 0 degree, force is 0. Right? So, very important point, force acting on a current carrying wire. This will be used in another derivation in future, force between two parallel current carrying wires. Okay, once we have understood what is the magnetic field due to a current carrying wire, once you do that, then there will be force between two current carrying wires, that will be done. Okay, move on with another concept, Biot-Savart's law. So, what is a Biot-Savart's law? So, Biot-Savart's law is basically, it talks about magnetic field due to a current carrying wire. So, it's basically going forward and coming back, going forward and coming back. So, first we started saying that a moving charge have its own magnetic field, and because of that magnetic field, it must interact with the external magnetic field. And then we said current carrying wire is motion of charges, so it will also interact with magnetic field. That means it should also have its own magnetic field. Clear? Let's go through this once more. Moving charge have its own magnetic field. Moving charge have its own magnetic field, right? So, if the charge is moving, it will have its own magnetic field. Now, because of this motion of the charge, there is a magnetic field, and if there is an external magnetic field present, then these two magnetic field, they interact with each other. Okay, and because of the interaction, the charge experiences a force. Charge experiences a force, right? That force is given by Lorentz force. Now we generalize that charge experiences a force, that can also be generalized to find the force acting on a current carrying wire. Current carrying wire is experiencing a force. So, what we can say, because it is experiencing a force, it must have its own magnetic field as well, because magnetic field can only interact. Electric field can interact. Electric and magnetic field cannot directly interact. There is an indirect interaction obviously, but magnetic field and electric field, they cannot interact directly. Okay, so that means the current carrying wire should also have its own magnetic field. There were two persons, Biot and Savart. Okay, Biot-Savart's law, this T remains silent. It is not Biot, it is Biot-Savart's law. Okay, Biot-Savart's law is basically two separate people. They came up with the idea how to find the magnetic field due to a current carrying wire, and later on the law was named after both of them. Okay, so the what was the law states? First of all, you need to understand there is a current carrying wire which is carrying some current. Okay, the wire shape is drawn like a snake. It is not a snake, it can draw any line, does not matter, as long as it's a non-regular shape. Okay, we are slightly trying to prove that it is valid for any shape. That is the reason we draw it like this. Okay, the shape is not important, major thing is that it should not be a regular shaped wire. Okay, current is being carried by this wire. Okay, and here this is the point, this is the element, this is called current element, because this is a not a regular shape. We need to take a small portion of the wire and try to find magnetic field due to that small portion. Okay, this element is being called as dl vector. Dl is the current element, it's called current element. IDL actually called current element. Okay, now current is being carried in this direction. Now we are trying to find the magnetic field at a distance r, magnetic field at a distance r from this point. Okay, this due to from this element, this is the distance r, and if you take the direction of dl vector, dl is a vector, right? Dl is a vector. So dl, suppose this is the dl. What is the direction of this dl? The direction of the dl will be along the tangent in the direction of the current. Current is in this direction, so you take a tangent at this point and take the direction along the direction of the current, then this represents the dl element direction. The angle between this dl element and this position vector is theta. Okay, this angle is theta, right? now we are saying that if this is the case, then the magnetic field at P due to this small element dl, which can be written as dB. dB is the dBp. dB is magnetic field and P is at point P. Okay, dB is a small magnetic field due to this small element. Okay, small magnetic field due to small element is proportional to the magnitude of the current. Is proportional to the magnitude of the current. It is proportional to the length of this current element. Is proportional to the length of this current element. It is inversely proportional to the square of the distance between the element and the point. It is inversely proportional to the square of the distance between the element and the point. Okay, and it is directly proportional to the sine of the angle theta. It is directly proportional to sine of the angle theta. Then combining these four equations, so if a quantity is proportional to more than one quantity, they can be combined and written in a single equation. So for example, suppose A is proportional to B, A is proportional to C, A is proportional to say 1 by X. Okay, then when you combine, then you can write A is proportional to B, C by X. Okay, and when you remove the proportionality symbol, you add a constant and you say B, C by X. Right, this is the constant of proportionality. This is how we generally write in proportion. So here also, so four quantities are there. So when you remove the proportionality sign, there will be a constant mu naught by 4 pi. So introduce our hero of the chapter, 4 pi upon mu naught upon 4 pi. So if you remember, in electrostatics we used to have a constant 1 by 4 pi epsilon naught. Right, in electrostatics we used to have a constant 1 by 4 pi epsilon naught. In magnetostatics, in magnetism, we will have a constant mu naught by 4 pi. So our old hero 1 by 4 pi epsilon naught is replaced by mu naught by 4 pi. So mu naught is saying epsilon naught, you are getting older, you go away. Now I am here, I will stay for longer than you. Okay, just joking. So mu naught by 4 pi is the constant of proportionality in magnetic fields. In magnetic field related expressions, this will come. Okay, and now I into dl into sine theta divided by r square. So all the direct proportionality quantities will be multiplied and inversely proportionality will be in division, right? So when you combine these two, you get mu naught by 4 pi I dl sine theta upon r square. And sometimes you might be asked to write in vector form. The vector form of Biot-Savart's law is given by dB equals to mu naught by 4 pi I dl cross r cap divided by r square. This is the general form. Sometimes we also write it like this, dBp, okay, equals to naught by 4 pi I dl cross r vector. Now because we have added a vector over here, that means we have increased the magnitude by 1. We need to divide it by magnitude, one more magnitude. So sometimes it is written like that. So either r cap r square or r vector r cube. Don't confuse. Remember, magnetic field is inversely proportional to r square. R cube we are writing only when we are expressing it in vector form and using r vector. Some books, some teachers follow this. Some books, some teachers follow this. Okay, I personally recommend this one. This one, do not alter the value of r over here. That's why this is my recommendation. But if you are in your college, or if you are in your textbooks or the books that you follow, they use this symbol, you might come and say me, sir, the book says r cube, you are saying r square. Make sure that you are checking whether it is r vector or r cap. If you are writing r cap, okay, r cap, it is actually r vector by r. It is a unit vector. That is 1, magnitude wise 1. So that's why it can be written like that. Okay. So remember this. This is the vector form of Biot-Savart's law, another super duper important part. So Biot-Savart's law as a statement is being asked. It can be asked as a vector form as well. So no matter what, if you are writing in this style, if you are writing dpp is proportional to I, dl I 1 by r square sin theta, then do mention what are these variables. What is I, what is dl, what is r square, what is sin theta, you have to, what is theta, you have to mention them. Otherwise, you need to write the everything in words. The magnetic field due to a current element dl is directly proportional to the current I. Magnetic field due to a current element dl is directly proportional to the length of the element. Magnetic field due to the magnetic field due to the element dl is directly inversely proportional to the square of the distance between the element and the point. Okay, and magnetic field is directly proportional to the sine of the angle between the position vector and the element vector. This is the position vector. This is called position vector r. Okay, r cap, and this is the element vector, which is dl vector. Okay, the angle, sine of the angle between them. So basically, this sine theta is coming from the cross product. Yes, because of the cross product, the sine theta is coming. If you are writing in the cross product format, the sine theta is not there. You might say, sir, what happens to the sine theta? Sine theta is getting absorbed by this cross. That's why sine theta is not appearing over here. Okay. Now let's see one question. The magnetic field at the origin due to a current element dl placed at a point with vector position r vector is. So same question as your that's why I told you both formulas, r vector and r cap as well. So if you see that here, r vector is given. First of all, you need to remember the order. Order is dl first, then r. Now if you are writing r vector, there should be r cube in the division. If you are writing r vector, there should be r cube in the division. Obviously I was there. Okay. Now if you see here, this is correct, order is correct, dl cross r vector, but here we have r cube. This is not correct. If you check this one, it is r cross dl, so this order is incorrect. Here also r cross dl, this order is incorrect. It will be dl cross r always. Now if you see the other one, the last one, dl cross r correct, and r cube is also correct. So just be careful. This is a very common mistake. Students think that it is r square, dl cross r cap, r square, dl cross r vector, r cube. Okay, because r cap is unit vector, it is not increasing the value. So here when you are doing r vector, that increasing the value by r times. So to compensate that, you have to divide by 1 extra r. Okay, so that's why there is a r cube. This is the correct answer. That's a very major common mistakes that everyone makes, right? Okay, so this is the end of today's session. If you want to download the PDF of this session, what you need to do, I told you many times before as well. You go to the description section of this video, click on the join free KCET batch. Okay, once you go here, click free AS KCET 2027 batch. You come over here in our section. Here you will get the batch. You need to register yourself using your mobile number and email ID. Once you have done that, you will get access to this batch. All the chapters, all the lectures that we are doing in our channel will be coming over here along with the class notes, etc. So you will be able to download them. You can watch the session as well. Okay, there will be support of Ved AI as well. You can ask the Ved AI questions related to the lecture as well, right? So that is very helpful for all of you. So don't miss out on that. And I'll be back with the remaining part of this chapter next week, next Tuesday. Till then, bye. And I'll be saying hi. If you are watching me in the live anytime, just say hi. I generally reply. But if you just come here to say 3 times that I don't understand it, then I cannot help it, because you have to mention what you have not understand. You have to watch it from the beginning of the session. If you come in the middle of the session and say that I do not understand it, I cannot help it, right? So start watching from the beginning. Once the live ends, you will get the access to watch it from the beginning. So do check that out. Till then,